Igneous Rocks Part 3-1, Bowen's Reaction Series. Bowen's reaction series can be described as the order of crystal formation from magma as cooling occurs. Now, you can see that it actually has two parts to it. There is the discontinuous series on the left and the continuous series on the right. In the discontinuous series, at a very high temperature, the first mineral to form is olivine. But as the magma continues to cool, some of that olivine will turn into pyroxene. If you remember, the pyroxene that you're familiar with is augite. As the cooling continues, that pyroxene will turn into amphibole. Amphibole that you all know and love is hornblende. The last part of the discontinuous series, the amphibole could turn into biotite. That is officially the end of the discontinuous series. However, sometimes the magma hasn't finished cooling down, and there's still plenty of liquid left. The liquid that's left, though, has aluminum in it, so it could make potassium feldspar, or it could make muscovite, or if it has lots and lots of just silica in it, it could make quartz. So ends the discontinuous series. At the same time the continuous series is going on, it starts off with the first mineral forming is calcium-rich plagioclase. Now, calcium-rich plagioclase is kind of gray in color. It happens to be called anorthite. As the melt cools down, the calcium is booted out of the plagioclase and replaced by sodium. So if there's enough sodium to boot out the calcium, by the end of the continuous series of the Bowen's reaction series, it is all sodium-rich plagioclase. And then, of course, the extra silica and the extra aluminum and such are all going into making the K-feldspar, muscovite, and quartz. So you're starting high temperatures, olivine, pyroxene, amphibole, biotite. Some of my students have remembered this order by going O, P, A, B. And they can remember that by remembering that old people are boring. Actually, all of this is not as confusing as it sounds, because it is all related to the crystalline structure of the silicates. And you already know that, don't you? Good old silicon tetrahedron, SiO4. And olivine has the isolated tetrahedra. That is, the tetrahedra would repel each other, except that they're being held together by iron and magnesium ions. Whereas the pyroxene is a single chain tetrahedron held together by other magnesium and iron to another chain. We've got our double chain, and finally we have our sheet, which you would find in the muscovite mica. O, P, A, B, as in biotite. But muscovite and feldspar and quartz don't have any iron and magnesium, so that's why they're not officially part of the discontinuous Bowen's reaction series. Olivine, pyroxene, the single chains, basically, if there's enough silica around and not enough iron and magnesium, then the single isolated tetrahedra will become single chains. And then if there's still plenty of silica left, the single chains will turn into double chains. And finally, the double chains into biotite. Time, it might be the end. They might have used up all the silica, all the iron, and all the magnesium. Or there might be plenty of silica left so that the other three minerals can form with the leftover silica, aluminum, and potassium. Meanwhile, of course, you've got your calcium-rich plagioclase, which is gray, eventually becoming your sodium-rich plagioclase, which is white, the kind of plagioclase that you had in your box of rocks. In the middle, however, you could have 50-50, or you could have 60-40. It's called a solid solution. Let's take another look at it in terms of the rocks that would be forming. Let's say you had magma with very little silica in it. It would start the Bowen's reaction series by making olivine and calcium-rich plagioclase, but then it would be done. all of its silica is used up, what kind of rock do you have? You have peridotite. Any rock that has lots of iron, ferrous, and magnesium, Ma, it would be ultramafic. So peridotite, the rock of the mantle, is ultramafic. If, however, there is some silica left, some of the olivine will turn into pyroxene and perhaps a little amphibole, and the calcium would pick up some of the sodium, and the result would be a mafic rock, M-A-F-I-C. That would be otherwise known as basaltic, and the rock that you would get would be either basalt, if it was a small-grained rock, or gabbro, if it was a coarse-grained rock. Let's say there's plenty more silica in that melt. It can go further into the series and get some amphibole and biotite mica created. Meanwhile, the calcium-rich plagioclase has turned into sodium-rich plagioclase, and you now have an intermediate rock, or an andesitic rock, like andesite or diorite. Finally, if there's a ton of silica left, it has not only gone through all of the Bowen's reaction series, but it can go ahead and make some potassium feldspar, muscovite mica, and quartz. Then you have a very felsic rock, feldspar and silica, which is also called granitic, and the two common rocks would be rhyolite and granite that you would form in that way. You can see 4 different columns. The largest column is the felsic column, and then you have an intermediate column, a mafic column, and the ultramafic column. Now, if you had a rock that was about 90% olivine and only 10% of the calcium-rich plagioclase and maybe a little pyroxene, that would be an ultramafic rock. What rock would it be? It would be peridotite. Let's say you had rock X. Rock X is about 20 to 25% quartz, about 20% potassium feldspar, 30 to 40% plagioclase, but it would be sodium-rich plagioclase, a little biotite, and a little amphibole. That rock would fit right here, and it would fit well within the granitic or felsic column. That would either be granite if it had large grains, or if it was an aphanitic, small-grained rock, it would be rhyolite. So what would you expect to find in diorite? Just look up. You would have well over 50% plagioclase feldspar. Not completely white, not completely gray. And the other half of it would be black because it would be amphibole and pyroxene. That is the content of diorite, or of the aphanitic version of diorite, the andesite. And of course, the mineral content of that would be intermediate. And finally, of course, gabbro would have some olivine, some pyroxene, and calcium-rich plagioclase, as would basalt, because they are mafic. There really is no common rock found that is ultramafic and fine-grained. There was billions of years ago, but the Earth hasn't been hot enough for billions of years to create a magma that could come to the surface with that kind of composition. This is really a useful chart. You'll notice that the silica content increases as you go toward the felsic. The potassium and sodium increases as you go toward the felsic. But if instead you go to the right, you are increasing the calcium, the iron, and the magnesium. You're getting more mafic. One last look at this chart. The discontinuous part of the Bowen's reaction series, OPAB, old people are boring, can be seen right in this chart. Olivine, pyroxene, amphibole, biotite, going from mafic to felsic. And then, of course, when you're done with all of the part of the Bowen's reaction series that has iron and magnesium, what do you get? Muscovite, potassium feldspar, and quartz. Even the continuous part of the Bowen's reaction series is here. Because what do you start with? You start with calcium-rich plagioclase, and you end with sodium-rich plagioclase. So this chart makes ever so much sense.